So we finish this up with lines and planes in space, and then we go into much more dramatical stuff when it comes to linear algebra. So how do lines and planes look like in space? So again, to finish up our multivariable section, we have our XYZ plane. Okay. So lines is just like multivariable. Given a point, we can make a line through that point, call that L, given a parallel vector, call it U or V or whatever you like. Okay? And that's how we do lines and planes. We'll talk about a little later. It's basically now just a perpendicular vector, but for now, parallel lines. So how to make a line is given a point and a parallel vector to it. And that's exactly what we need. So given any point, P naught, and having a direction vector U, any point on the line is given by this portion here. Okay. Now to break this down into more abstract thought is, since the P is on the line, a line L, therefore we can rewrite these portions as these one situations here, where the difference between x and x naught is t times u1, and so forth, using our vector u here. Okay. Now, in most cases, we don't really use this aspect of this definition. We use its parametric equations instead. That's much more abstract and more back into the multivariable course process. So given a vector u and a point on P naught, therefore we have the parametric equation of a line is given to be this, where x naught, y naught, and z naught are the initial point in our value. Okay? And this is any arbitrary point on the actual line at that point. So this way it gives the entire line of the parametric equation. Okay? And again, t is just an arbitrary t value, right, with our vector u. Okay. So that's mostly the general one we always see, not usually this type of format here. But it's very straightforward, right? You just add it over, and that's how we prove the parametric equations. So just a quick little example here how we do this. So given a point P naught and P, so given two arbitrary points, find the parametric equations for the line L through the 2 points. So if you want to find this, we have an initial point already. So here's our initial point. Well, really, we could pick any point we like, but I'll just use that one just for practice sake. And now we have, we need u. So we need our vector u. Okay. So to find our vector u, we go up here, and we just do our vector there. So it's P naught to P, so it's final minus initial. So how to find this vector? We go from here to here, so 4 minus 2 is 2. 2 minus 4 is negative 2, and then finally 5 minus 8 gives you negative 3. So there's our vector u. Okay. So therefore our parametric equations is equal to, well, x naught, I just chose this one, so to use that one. So 2 plus 2t, y would be 4 minus 2t, and then z would be 8 minus 3t. Okay. Now, the next one's a nice, interesting one. Does the line L intersect the xz plane? Sorry. If so, find the point of intersection. Okay. So for this one, let's just go over visualization. What's going to happen here? So this is an interesting part. So we're talking about the xz plane. So this plane right here, right? This flat surface going in this direction. So given an arbitrary point on that, so what does that look like? Well, that's some point x, comma, something, right? Well, some value z. But the key thing is y is actually 0 because it has nothing to do with the y-axis, right? It's just simply just like the xz plane, kind of like the xy plane, right? If I break it down, z is basically 0 in this point there. And I can go all the way around. If it's the point here on the zy plane, therefore x will be 0, and vice versa. I just move it all the way around. But for now, we're asked to find the xz plane. Okay, so first we're going to write down our information, right? So let's see. So basically, is when is these points intersect, or when does this line intersect this point here? Okay, so first thing we're going to find t, right? Those are our main focuses. And unfortunately, right, these are arbitrary x and z values, so the only really number we have is y equaling 0. So that's the only one we can use, which means we could just solve for t using just our normal equations. So subtracting the 4 over and divided by 2, we get 2 is equal to t. So therefore, at that point, we could find the actual intersection. We just may plug it in t for x, y, and z. So our P1 is where they actually, so yes, they do. So we would say, yes, it does actually intersect because we can find it. So if, for example, if it was an arbitrary value, we couldn't, but because it's actual only one plane, we can, meaning kind of does like that, for instance. So I'll plug in 2, we get 4 plus 4. 2 is 6. This is going to be 0, obviously, because we have a 0. And then plug in 2 in for t here, so that gives you 6. So 8 minus 6 gives you 2. So the point of intersection is 6, 0, 2. Interesting example. I always like that example to show you guys how it's going to go. Okay. So then we go into normal vectors. So like I said, those are lines we're going to now at planes in three-dimensional space. So normal vectors, a vector is said to be normal if it is perpendicular to a plane, or another word, orthogonal as well, meaning the vector is perpendicular to any vector. Remember, like I said, means orthogonal, hint, hint, right? So in this case, our normal vector is called n, for arbitrary, if and only if, again, going back way, way, way back to this section, the dot product is actually 0. Okay? So again, little review of multivariable is here's our plane, and we have a vector n that is perpendicular to that plane. Okay? So for lines, we need parallines. So little fun fact, right? Lines, we need a point and a parallel vector. Here's the opposite. We need a point and a perpendicular vector. So complete as opposites, right, when it comes to lines and planes. Okay. So formal definition, let Q be a plane containing the point P naught and having the normal vector A, B, C. A point P is on the plane if we have this situation happening. Again, key thing is normal vector, right, perpendicular. All right, so let's again try some examples on this. So find the equation of a plane containing the point P naught and having a normal vector n. So we don't have to find it. It's already given to us. And according to our definition, that's our ABC there. And our point is going to be x naught, y naught, z naught. So just following this format. And there we go. Or if you like, you can rewrite it in its natural format, distributing and bringing the constant over to get to the d value. So it looks exactly like multivariable. I think it gives you this. So now what if you have to find the actual normal vector? So given the plane equation, so we are given a plane equation already. Find a normal vector and find the unit vector. So find the unit normal vector. All right, so again, already knowing that this is a plane, so therefore we can go backwards, right? So our normal vector is going to be 2, -1, 4. So find the normal vector, check, that works. And now we want to find the unit normal vector, so remember to do that we need basically to do this. Well, just put that on top. So we need to find the magnitude of n. So 2 times 2 is 4, -1 squared is 1, 4 squared is 16, so 5, so it's 21. So our normal vector, I call it W in this case, remember we defined it earlier to be normal, is equal to our vector times our magnitude. And there we go. Both of those are done. So, two different cases when given to you, find a normal vector, right? The even normal vector. But the question is, well, how do I go from scratch? Well, how do I find the actual vector itself that would use that process? And that goes back, again, knowing that the cross product automatically gives you a perpendicular vector, which is kind of nice. Okay. So again, a visual representation of what's actually happening here. So give it a plane, or 1 point on there, or actually, say 2 points on there, so P1 and P2. Okay, so all these are perpendicular to each other, which is perpendicular to this normal vector here, which is going to be the cross product. So I guess I'll just write it all out. Of that. So first we got to find these vectors, find the cross product, and that guarantees our normal vector. And then we can replug in our equation to find the plane itself. Okay. So just more work, that's all it really is. But it's not too bad to deal with. So find the equation of a plane passing through the points P0, P1, and P2. So just like this process, we're basically just going to find that. Okay. So let's first find our two vectors. So again, initial minus last. So 2 minus 1 is 1. 0 minus 3 is negative 3. Negative 1 minus 2 is negative 3. That's our first vector. And then P1, P2. Oh, sorry, P0. What am I doing? This is P0. Because I'm going from here to, yeah, that's right. Oops. Okay. What was that way? 4 minus 1 is 3. 5 minus 3 is 2. And then finally, 1 minus 2 is negative 1. Okay. So I'll call this U and B just for abbreviation purposes. So the cross product I'll put this one on top. Okay, so after doing this cross product, you should get this. Okay. So remember, this is our actual normal vector now. This is n in our situation up here. So now we just go back to what we did in the last two examples. So this is A, B, and C for our vector format. And we'll use, I guess you could use that one. I guess it really doesn't matter which ones you use. You get the plane, you're just going to give it arbitrary points in the plane. It's just the same plane. So they get this plane itself, but yeah, it's the same thing. No biggie. Plus 2. So minus 2. All of it there. And there we go. So parallel planes. So this is something you don't really do too much in multivariable, but it's actually a really cool concept. If you like the Marvel movies, this is actually a really cool concept of the multiverse. And if the multiverse actually does exist, this is probably how you could prove it does exist, believe it or not, with parallel planes. So parallel planes is just like parallel lines, right? These lines just never intersect. So now we just have sheets of paper. So literally think of sheets of paper stacked on top of each other. Those are called parallel planes. Just literally right stack on top of each other. So you think of just layers of piece of paper right on top of each other. So fun little fact, right? So if you think of the multiverse, you could think of it this way, where Earth 66 is on here, and then right underneath it is Earth, let's say 67, or arbitrary one right above it is 65. And the slightest, tweak or slight movement from parallel means now you have an intersection point or intersection line. And that's where, now one goes into one dimension and vice versa. So that's pretty cool when it comes to it. So a lot of people think, that's why deja vu comes into play, where you've seen this before. It's like, oh, your double ganger, I've seen this before. You have a double ganger out there. It means, you can see your other half that looks identically like you. But, it's a fun little concept, very, very theoretical. But it's really cool how to, you can actually do this or, explain this kind of stuff mathematically, very theoretical. Cool stuff. Yeah. Right, anyways, so planes are parallel to each other if the normal vectors are scalar multiples of each other, okay? Which makes sense, right? So just like parallel lines, so here they have the exact same slope, just different y-intercepts. So ideally, same slope. Here, you basically have the same slope, but just the scalars of each other. That's all it really represents. Okay. So here's an example. So given the plane equation, so we have a plane equation, find a plane that is parallel to this one with the given point P naught. Okay. So we got to find another plane. So here's our first plane, another plane right on top of it. Okay. So again, we're just going to follow this logic here. So first we got to find our n, or vector. So 6, -4, and 2. Okay. Now, question now becomes, well, how do I get the point, right, from here to here? Right? So, ironically enough, this point doesn't actually matter, right? Because it could be any arbitrary point, let's say here, right, which is away from the original plane. And it's some distance above it or some distance below it. All I care about is a plane that's all right, so applying it, and it's tilted the exact same movement, not tilted this way, right? It doesn't matter if my point is here on this my pen. If I tilt it this way, tilt it that way, it still hasn't moved, right? It's still there. What's moved is the actual plane itself. So really, you get to choose any constant you want because you're just scaling up and scaling down. So we'll just use 2, for instance. So if I use c equaling 2 and follow this format, well, my new scalar, not scalar, our new vector would be just times it by 2, so 12, -8, and 4. And we'll just use that one with this point. And there we go. And again, you can pick any number because it's just a scalar multiple of it, which is the best part. So now, are the planes, this one, parallel to each other or not? Or how do you find if they're parallel? Well, this process exactly tells us right here. All they do is be scalar multiples. Well, let's see. So first plane is 4, -8, and -6. Second one is 3, -2, and 1. So the question becomes, well, are planes these parallel to the first one? Sorry. We want to see if they're parallel to this one. Sorry. This one. Okay. So let's see. Is there any way I can multiply a constant to this to give me that? So let's see. Looks like if I multiply this by 3, or -3, get from here to here, and it has to be the same constant. So -3 times -4 should give me 12. So nope, that doesn't work. Let's see here. So again, constant can be actually a fraction as well, right? So if I cut this in half, so divide these by 2, I get exactly those. So this one's a yes because of it. So these two are parallel, those are not. So somewhere they intersect. We can actually find it if you really want to as well.